SPD, but the PF3 molecule is only SP3.
PF3. You have to draw it out.
Did I just out myself for getting something wrong?
Yeah, because this is, well, that's correct. Yeah. And then this, I think you're just missing a pair of electrons. This iodine brings 7. So 1 in bonding, 2 in bonding, 1, 2, 3, 4, 5, 6. And then I3, so there should be a second lone pair on there.
Perfect. Thank you. I was like,
Yeah, more people got those wrong than I might have expected, but. My allergies are like out of control today.
They've been really bad.
Like what is up? Because I thought I just had like indoor allergies. But
Everybody looks at me like I have a plague.
I know. Oh. I even took my allergy pill this morning, but it does not seem to be kicking in. No input is detected. That's not good. Oh, because I didn't. Question?
Yeah. Do I have these labeled wrong? Because I thought that this would be the P with 3 fluorines around it, which would be that.
And then you have to draw it out because it actually has a lone pair too. So it'd be this one.
Okay.
Yeah, and then same with this one. I would draw it out and count your electrons because I think you have 3 lone pairs on the iodine plus 2.
Okay.
So that puts it into 5.
Gotcha. Okay. So it leaves, with that lone pair, it leaves the possibility of another bonding.
Yeah, and it's
Okay.
also like the geometry because you have to take into account like the space that that lone pair is occupying.
Okay. Yeah.
So sigma and pi orbitals are different from sigma and pi bonds, is that right?
I mean, I guess you can have a sigma bonding and like pi anti-bonding.
I don't understand that answer.
Because, right, you have orbitals, and first you have to, like, they get two different labels. Because they get either like a sigma label if they're head-to-head, and then if they're in phase, then it's bonding, and then if they're head-to-head, it's still sigma, then it's just anti-bonding. They're not in phase.
So the bonding and anti-bonding are not considered orbitals?
Not really, because you have to, that's just like a description. Because like you have to have, like you have a bonding orbital, right? So then you have to say if it's bonding sigma or bonding pi.
Yeah, it's still confusing. I don't like the way that wording is confusing.
Yeah, when they overlap, that is implying that it's favorable, so that they're in phase.
But if they're in phase, aren't they bonding?
Yeah, so then but then they can't be bonding and anti-bonding.
Oh.
Yeah, so it's kind of like asking, you have like some sort of carbonyl molecule bonding, like what is that?
So when they overlap, they're not antibonded?
Yeah, usually.
That was kind of the clue on that one, I think, that I missed.
Thank you. I was gonna ask for this. Great.
Girl Scout
All right, I guess we'll go ahead and get started. So a couple of announcements. So don't forget, today is Clubs Day on our campus. Of course, we kind of have class during it. But after this, you can sneak out. So Clubs Day, it's from 12 to 2. I think it's in HEC 129, if I remember correctly. Probably just a big room downstairs. And there's supposed to be food, so you might want to check that out. I'm also pimping out Earth Club, so I'm the Earth Club advisor. And we're starting to plan for our big Earth Day event, so I think that's April 21st. And we'll do something to celebrate Earth Day. So if you want to join Earth Club, you can always email me. We also plan like hiking events if anyone's interested. And you could really do whatever you wanted to with the club, since you'd be the students. And welcome on chat. I see people online, so if you're online joining us, just say hi so I know you're alive. Other questions before we get started? Questions about last week's material, the quiz, or anything? Then I have papers to hand back, so if I didn't catch you during class, I'll try to catch you during lab. Also, today's lab should be pretty fun. We're doing a distillation lab. Just obviously, we'll talk about this in lab, but don't eat or drink anything we play with today. All right, so let's move on, I guess, to chapter 15. And so I feel like chapter 15 complements our gas law chapter pretty well. So gas laws, we took a very idealized look of the science and these intermolecular forces. We said there were none. But now we're going to be looking and seeing, well, what were those intermolecular forces that we kind of glossed over? How can we at least make some predictions and talk about them? Do we have questions or anything? Questions? All right, just let me know if we want to go over anything. And so we're saying that the chemical composition and molecular structure of a chemical species determine the type and overall strength of its intermolecular forces. And so notice the term intermolecular forces. So that means that those are attractive forces that exist between all molecules. And so to help you remember, right, just think of your interstate highway. That's going to be between states. So that connects our states just like these intermolecular forces, again, connects different molecules. And this would be different from like intramolecular forces. And so those are what hold the atom together, so everything that we've been talking about, right, our sigma bonds, our pi bonds, so all these would be intramolecular forces. So we're not talking about those, we're not breaking molecules, we're not breaking bonds, we're just breaking the attractive forces between the molecules. And I'm just making this distinction because even in organic chemistry, people use like the wrong terms, that you're breaking bonds when we're talking about intermolecular forces, again, between molecules. And so these intermolecular forces are the forces that hold liquids and solids together, so that's why like water, for example, is a liquid at room temperature. We'll go into kind of the abnormalities of water. And so that means that our phases then, so whether a compound is going to be a solid, liquid, or gas, that depends on, of course, the magnitude of these intermolecular forces between the particles and then relative to the amount of thermal energy. So increased thermal energy, we said, right, that gives us more kinetic energy with our gases. They start to move faster, and so that can, of course, start to disrupt intermolecular forces. And we've just kind of seen this general trend. So if energy is high, then matter tends to be gaseous. And when thermal energy is low, matter tends to be a solid or a liquid. Again, just very general trends. And so now we'll kind of look at our three phases of matter. And so if something is a gas, that usually means it has a low density. And we know the shape is indefinite, the volume is not defined, and then that probably means that there's going to be weak intermolecular forces, because if it's a gas, right, they're far apart. That's why we even ignored those intermolecular forces in our gas chapter. And then once something is a liquid, then that has higher density. We said still undefined shape, as there's enough movement for those molecules to kind of slide past one another. But now it has a defined volume, and now it's going to have moderate intermolecular forces. Again, that's what's going to drive cohesion. And then compared to a solid, so that's going to have a high density, a definite shape, a definite volume, and of course strong intermolecular forces. And so this is just a comparison for water. And of course, water is, again, kind of abnormal. And so the gas and liquid phase are pretty much what we expect. So gas, we know that it turns into a gas at 100 degrees Celsius. Here's its density, so very low density now. And of course, it would look very far apart in kind of our molecular view. And then a liquid, this would be at room temperature, so 20 degrees Celsius. It has a density of about 1, so that's why water is kind of our standard of 1 gram per centimeter cubed, or 1 gram per milliliter. Of course, we know our molar volume be 18 milliliters for 1 mole. And then ice is a little different. So ice, what do you know about ice as compared to other solid state structures? So what's the funny thing about ice? So exactly, so ice is less dense, so that's not what we expect. So this is kind of not the norm. So less dense than the liquid. And water just starts to take a tetrahedral solid state structure, and so it ends up taking up more space. Let's just pull up a picture. So this is probably a good picture. So there's our oxygen, hydrogen, and so just kind of repeating units of this tetrahedral structure, and so it ends up being less dense. Here's another comparison. So again, explaining how the liquid water, they kind of rotate around and have a density of 1 gram per milliliter, while ice, again, they take a more defined solid state structure and ends up taking more space. So that's not normal. That's not normal what solids do. They usually kind of pack tighter than their liquid counterparts. But again, ice is one of those exceptions. And so this is kind of review of just our states of matter. So like we've seen again with liquid, that these liquids, that the particles are closely packed, but again, they have the ability to slide past one another. And so that means that our liquids, of course, are incompressible, but they still don't have a defined shape. So then they have that ability to flow. And so if we look at the properties of liquids, so liquids have higher densities than gases, and are incompressible since the particles are, again, closer in contact. And again, we kind of mentioned that with our gases chapter, that they started off as an ideal gas until we start compressing them, and at those higher pressures, now those particles are closer in contact to where the fact they start condensing as a liquid. And again, they have that indefinite shape since they still have translational freedom. So again, flowing around, sliding past one another. But again, defined volume, since they have close contact, and so now not only are they kind of holding each other together in their condensed form, but we also can't compress them like we can with the gases. So the gases, so we just finished our gas law chapter. And so we had said in our gas state, particles essentially have complete freedom of motion. So we mentioned they're just bouncing around, constantly moving. And again, we kind of said that they were not sticking, so we really didn't account for those intermolecular forces. And so we said because of that, gases just expand to fill and take the container of their shape. And so there's a large amount of space, like we said, so that's why, again, we mainly said intermolecular forces were negligible for our gases. And then again, gases are compressible, but like we are understanding, there is a limit. And so again, you've probably seen those liquid nitrogen tanks. So they get compressed, compressed, compressed to liquid nitrogen. And then of course it can re-expand and come out either a gas or a liquid, kind of depending on the nozzle, what the pressure is set at. And again, this is comparing liquid versus gas. So liquid not compressible versus a gas with all that empty space is highly compressible, again, until we reach essentially the liquid phase. And so solids, if we think back to our first quarter, again, we said they were packed close in fixed positions. Obviously, right, there's still electron movement running around the atom, but otherwise, right, our molecules are mainly staying in place. There's going to have some vibrational freedom and rotational freedom, but otherwise they're static or have limited or restricted movement. Again, they can kind of stretch their bonds a little, some wagging motion, but they're not really, again, moving anywhere. And so because they're not really moving, that means that they retain their shape and their volume when they are placed in a new container. And so solids don't flow. And so solid particles can be arranged in either a orderly geometric pattern, and that would be called like a crystalline solid. So, you can grow like nice table salt. You could even take, salt or sugar at home, dissolve it, make a supersaturated solution, and then you could make like rock candy. So that would be an example of a crystalline solid that you could do, at your house. But any solid particle that does not have regular geometric pattern, that's just an amorphous solid. So that could be, just your regular, like more powdered sugar, just to compare. So that's going to be more amorphous, right? All finely ground, doesn't really have a crystalline composition. If you look at probably just like regular sugar or like that organic brown sugar, just those kind of have nice little crystalline solids. And again, you could grow it into a big crystal. Other solids that just have more amorphous structure would be plastic and glass as well. Again, just they're not one big crystal, just kind of this amorphous solid. Let's skip this for now. Let's talk about intermolecular forces before we go into all the math. And so now let's talk about these intermolecular forces. So again, these are the attractive forces that hold matter together, that hold different molecules together. And so all attractive forces between particles are electrostatic in nature. So what does that mean if something's electrostatic, just simple terms.
It wants stuff to come to it. It wants to go to stuff.
So why does it want to go to stuff there? What does it mean if it's electrostatic?
Positive and negative charges attract each other.
Yeah, so just positive versus negative charges. So we basically need some region that's kind of negative and some region that's kind of positive. And so the strength of the attractions between these particles of substances determines its state. And again, we'll look at these electrostatic forces and see whether these kind of negative and positive regions, whether they're temporary, whether they're permanent, and that will also help determine the strength. So that's why we've been kind of looking at polarity too, because it'll come back to haunt us here. And so you'll kind of get a sense for this as we go through the attractive forces, but we'll see at room temperature, we have moderate to strong attractive forces result in materials being solids or liquids. And in general, the stronger the attractive forces, the higher the boiling point of the liquid and the melting point of the solid will be. And again, they vary, so we'll look at them weak to strong, how to order them roughly, and how to kind of predict. And yeah, so it depends on the kinds of particles. And again, the stronger the attractive forces, the more the particles resist moving. And so this also means the stronger the attractions between the atoms or molecules, the more energy it will take to separate them. And so that goes back to, right, our kinetic energy being related to temperature. That's why we say you heat things up, and it tends to be more of a gas. And so boiling a liquid requires adding enough particles to overcome all the attractions between the particles. And it reminds us, however, we're not breaking the covalent bonds, so aka we're not breaking any intramolecular forces. So the higher the normal boiling point, the stronger the intermolecular forces. And so we had answered why are molecules attracted to each other. So we said that it's basic attractive forces between opposite charges. So we've seen the extremes of a cation with an anion, right, to make our ionic solids. Now we're going to see kind of polar molecules and how those have a permanent dipole and how those will be attracted to each other. So such as a case of water. And again, this is just a preview. We have oxygen and hydrogen here. So we said oxygen, right, is very electronegative, so it's going to strip off that electron density from the hydrogen, and hydrogen only brought one electron to the party anyways, so this would be an area partial positive. The oxygen is, of course, partial negative, and now we would have this intermolecular attractive force between our other water molecule, so this is our partial negative region. And so we have partial positive, partial negative. So that's going to be our attractive force here. And so this is a hydrogen bond, but again, we'll go over them all in detail in a second. And so we'll look at how even nonpolar molecules will have these temporary charges, and we'll look at what that means. So a larger charge, of course, means stronger attraction, longer distance. It means a weaker attraction, so you even saw that, like thinking back to WebMO with your bond links, how some were longer, some were shorter, and that depends right on those attractive forces as well. And so intermolecular forces are smaller relative to bonding forces, since of course that intramolecular is between atoms. All right, so let's start with the weakest. So we're going to start with our dispersion forces. And so these, you might see them called different things. So they could be called dispersion forces. Their kind of full name is London dispersion. So you might see that term. Or they're also known as van der Waals forces. And so let's look at I guess we'll read the text and then we'll look at the picture. But basically we're saying we have a nonpolar molecule. And we could look at like helium, argon, so something like that. And let's look at the picture. And this is just basically like a snapshot in time. So we're looking at helium for a second. And you know those electrons, right, are running around that s orbital. And let's just say you could take a snapshot and kind of freeze the electron movement for a second. And let's just say we took a snapshot. And well, if we look at this, we have our electrons. They just so happen to be on the left side of this one. So this kind of gives us our area, a partial negative. Again, just because temporarily our electrons are on that side. Then if we look at our next one, let's just say our electrons are also on the left side. So now we have our partial negative region now next to this partial positive region, right, since these electrons happen to be on the other side. And then let's just say their neighbor is also looks similar. So again, the electrons just happen to be on the left side at this instantaneous moment. So now we have our partial positive region next to our partial negative. And so now we have, right, your attractive forces there. And so this is just the instantaneous dipole that's created. So we know that this is not a permanent dipole, so this is going to be weak. And so if we go back to the text, right, again, this is just a snapshot. You could just have a region with excess electron density, and anything with greater electron density, that's going to have your partial negative charge, again, just temporarily as it moves around. Then it'll be potentially next to another region with depleted electron density, again, just like we've seen in this picture, with a partial positive charge. And so you get attractive forces then caused by these temporary dipoles called dispersion forces, or again, London dispersion or van der Waals forces. So again, it's a temporary dipole, and then of course these electrons will move around, and you know, if they kind of move in sync, it'll kind of keep that dispersion force. Otherwise, right, obviously it's very weak, so they'll move around, they'll kind of be lost until it happens to, again, line up like that. And so the key part of this is, will all molecules and atoms then have dispersion forces? Again, it's the weakest, so if you have, you know, polar bonds or hydrogen bonding, it becomes less significant, but all atoms and molecules have them, including nonpolar ones, so you have to account for it. And so let's look at some trends. So if we just compare then all the noble gases and its boiling points, we can see the effect of molecular size then. And so it also depends like how much surface area there is for there to be attractive forces. And so as molar mass increases, the number of electrons increases, and this gives you, of course, a larger electron cloud. And so your strength of your dispersion forces increase. And again, there's also just more surface area. So xenon just gets larger, so it has more surface area to attach to another xenon. And so again, you have this mass effect. So helium has the smallest mass and has the lowest boiling point of 4 Kelvin. Then if we go up from there, so neon is about 20 grams per mole, 27. Then you can keep reading the chart all the way up to xenon. So it has the greatest molar mass of 131, and then also has the greatest boiling point of 165 Kelvin. So questions on mass. So greater mass, greater boiling point. And so now we can look at shape. as well. So it also depends, again, on that surface area. So now if we're comparing mass, so that's the first thing you should start off with. So we're comparing N-pentane versus neopentane. And what's the term for these when they have the same kind of formula but different shape? Isomers. So these are called isomers, or structural isomers. So we're looking at these two isomers, so they have the same mass. And so they're both pentanes, so they're both C5H12. But if we look at N-pentane, so N-pentane means this straight chain. And so if we're comparing, right, there's a larger area for interaction, so all those intermolecular forces, so they're kind of lined up. You can kind of have this stacking effect too. Well, if you compare it to neopentane, so that's more like the ball structure of it, where you have this one carbon in the center attached to 4 other carbons. And so you have a lot smaller area for interaction. And so again, you see that reflected in the boiling points. So neopentane, smaller area for attraction means lower boiling point. So 9.5 degrees Celsius versus pentane, which is 36. And so the alkanes all follow this trend. So with your increasing molar mass, that just means you have stronger dispersion forces. And so you have, right, pentane down on the bottom versus like octane, for example. So this is your fuel over here. So that's a bit higher boiling. And of course it can continue on, so nonane, and obviously increasing boiling points. So, questions? And so again, just note, so that means branch chains have lower boiling points than straight chains. So now let's look at dipole-dipole interactions. So this is our second type of intermolecular force. So they're, again, just called dipole-dipole interactions. And so this is why you want to be able to identify your polar molecules. And so now the difference between our van der Waal versus our dipole-dipole is that polar molecules have a permanent dipole. So they always have some region that has that higher electron density, either from lone pairs or like oxygen atom substituents. And so, of course, both the bond polarity and the molecular geometry determine the polarity. And this separation of charge is referred to the dipole moment. And I always encourage you, you can always, look on Wikipedia, look at the dipole moment to kind of help you put this in context. And we'll probably pull it up. And so let's look at some comparisons. And so, of course, this permanent dipole adds to the attractive forces. And this, of course, raises the boiling points and melting points. And so if we compare formaldehyde and ethane, for instance, so again, first thing you compare, well, are their masses different? And so their masses are pretty similar in this case, even though they have different formulas. They're both about 30 grams per mole. Except formaldehyde, right, has a CO bond, so this carbonyl group. And so what do we say about formaldehyde? Do we think it's polar, nonpolar? I see a lot of nods. So nods for polar, right? So it's polar. And we can, draw your Lewis dot structure. So we know, right, oxygen is getting the electron density. And so if we compare their boiling points, ethane has a boiling point of negative 88 degrees Celsius versus formaldehyde, which is negative 19. And so again, that big difference is simply due to the dipole moment. And so ethane, so this is completely nonpolar. So just CHs. Now let's see if we can pull up. Again, just so you have some numbers in context. So here's its dipole moment. So that's relatively high. So 2.33 for formaldehyde. So ethane, I'm not sure. Let's ask Google. I bet it's 0. Yeah, so it's pretty much 0. So again, just meaning no dipole moment, not polar, what we expect. So you can just see that in context. And let's put some of these in context. And so now we're looking at this chart. And so you could kind of guess it based off of your drawings. So it starts with propane. And so again, we can kind of compare all these since they have the same masses, or at least really similar masses, of around 44 roughly for the most part. And so they have them plotted by dipole moment. And so propane, we would expect to have a dipole moment of about 0, since it's just our 3-carbon chain. And then if we look, so the next one is dimethyl ether. So that's going to look something like this. And so what you'll kind of notice, so like ethers tend to be kind of not as polar. You have like an oxygen in the center. And so you can also, again, look this up to help you. So kind of the key point, right, is you want to be able to draw this structure so you can kind of recognize, yeah, there is an oxygen in the center that might have more electron density. And let's see if we can put it in context. So Wikipedia has a dipole moment for us, so 1.3. So again, that gives us a sense kind of lower on the polarity scale. And again, we see that slightly higher boiling point. And then you have these groups where you have this like more carbon or oxygen kind of in this triangle looking thing. So this is ethylene oxide. So it looks something like this. And so this is called an epoxide group. But epoxides, since they do this weird like triangle thing, they kind of stick out more than the ether. So they tend to be a little bit more polar. And we can again compare on Wikipedia. So again, here's ethylene oxide with that kind of different structure compared to our dimethyl ether. So now it sticks up more. So, you know, because it's kind of sticking out more, that makes it just a little bit more polar. And again, let's get a number. So they have the dipole moment as 1.94. So we're increasing polarity. They have it 1.89. You know, again, just rough estimates. It depends on how they computed this exactly. Then if we look at acetaldehyde, so let's plug that in to Wikipedia. So now we have this aldehyde group where you have, again, the carbonyls kind of sticking off at the end. And so again, that makes it polar. Again, you have the oxygen now on one side of the molecule. So increasing polarity, so now 2.7. And then the highest one over here and most polar is acetonitrile. We've kind of looked at acetonitrile before. And so the significance of acetonitrile, you could draw out the Lewis dot structure, and you'd also have your lone pair on the nitrogen over here. So we can tell it's really polar, right? Just to one side, though. And so that makes it even more polar. Where's the dipole moment? There we go. I don't know why this one's not in the chart. And so this one is 3.92, so now that's, again, more polar. And so now it's kind of the most polar. And even though this one has a slightly lower molecular weight than the rest of them, it has the highest boiling point since, again, most polar. So does that kind of make sense? So on an exam, I'd only have you kind of compare, one trait at a time roughly, since you have to think about molecular weight and structure and polarity.
Is the dipole moment just the oxygen?
Well, the dipole moment just like measures how polar it is basically, but you're right in that it's basically kind of based around the oxygen, because that's what we've been looking at here. So, right, your polar groups could be oxygen, nitrogen, fluorine. It just so happened we were comparing a bunch of oxygen groups, but then you can see how like moving the location of that oxygen, right, makes it more and more polar. So it started off in the center, and that was weakly polar, and then we either had it off to the side, or we switched the oxygen for a nitrile group, but now it's on one side with the lone pair.
Why does moving it make it more polar?
Well, you have to just think, it's like the electron density map, because right, if you have kind of oxygen in the center, well, now it's like pulling the electrons towards it, but kind of even out, versus if you have it off of one side, then you're really going to have like half of your molecule nonpolar, and then this half like wanting electron density. Yeah, so that's why I encourage you to look at the dipole moments so you can tell like what's been determined experimentally as you get a better feel of kind of drawing it out and how that would change the polarity. Any other questions on kind of these trends and polarity? And so now we have kind of our special case. And so this is, now we're looking at hydrogen bonding. And so yes, it's still a dipole-dipole interaction, but now you have kind of this extra phenomenon. And so when you have a very electronegative atom bonded to hydrogen, it strongly pulls the bonding electrons towards it. And so this is only when it's bonded to oxygen, nitrogen, or fluorine. And so we kind of mentioned this earlier, but again, here's what's going on. So hydrogen, right, it only has one electron. And so when this electron is, of course, pulled away, such as in, water, so now we're kind of back to water. So now it's being pulled towards the oxygen, except this leaves the hydrogen very exposed, and it becomes, they say, de-shielded, which just kind of means it's exposed electronically. It doesn't have any electron density around it, so it makes it very susceptible. And so this essentially makes this proton a very strong center of positive charge. And we mentioned again that oxygen, or if we had fluorine or nitrogen, again, they're very electronegative. They're pulling all the electron density towards it. And so you have, right, this electrostatic potential map where the hydrogen is basically stripped, and so that's why it's very blue. It's a very positive region versus this very large red region where our electronegative atom has all the electron density. So again, write that down, that this is only when hydrogen is bonded to fluorine, oxygen, or nitrogen. That's when you have that hydrogen bonding. And so this is even stronger than just your regular dipole-dipole. And so I'll go back. So this is basically our strongest force, at least of the three.
Fluorine, oxygen, and what?
Fluorine, oxygen, and nitrogen. I'll let everyone copy that again. And so again, these are very strong intermolecular attractive forces, so they're stronger than the dipole-dipole or the London dispersion forces. And so we'll see that anything that can hydrogen bond will have higher boiling points and melting points than similar substances that can't. And then this is still emphasizing, while these hydrogen bonds, even though we're saying they're super strong, they're nowhere near the strength of a chemical bond. And so they're only 2 to 5% the strength of a covalent bond. So just putting everything in context there. And so now we're comparing ethanol versus dimethyl ether. So ethanol has an OH group. So I'll just redraw. So here's ethanol versus that dimethyl ether, which just has the oxygen in the center. And let's see if we can look up. You can also see ethanol. Let's just compare its dipole moment. So it's not too crazy on the dipole moment, 1.69 for ethanol. But then we still get a huge difference in boiling point. So again, compare their masses first. So they have about the same mass. So we wouldn't expect them to have different boiling points, except this huge difference is just caused by the hydrogen bonding. And so you can see, right, even the dipole-dipole doesn't offer enough explanation. So just going back, we had said, so dimethyl ether was about 1.3. Ethanol, I think I said, was close to 1.9. So not too different, but it's all because of that hydrogen bonding now. Is you can have very strong hydrogen bonding interactions with ethanol. And so that gives it a big boiling point difference. So ethanol having a boiling point of 78 versus dimethyl ether of negative 22. Yeah.
Aren't hydrogen bonds covalent bonds? Aren't they sharing an electron with the atoms that they're bonded with?
So we're talking, so a hydrogen bond would mean that, so this is a covalent bond, but then a hydrogen bond would now be the hydrogen bonding with like another oxygen of ethanol.
Like on a different molecule?
Exactly,
Got it.
yes, on a different molecule. So that's the difference. Now we're hydrogen bonding here. So there's that hydrogen bond formed between your hydrogen and now your other oxygen from another molecule.
So the hydrogen and the oxygen in one molecule of water is a covalent bond, but when they're bonded to other molecules of water, it's now just a hydrogen bond.
Yeah, so let's redraw that. So we have, or kind of put everything all together. So right, this is our sigma bond. So we've said that before previously, right, there's just a single bond. We could look at the orbitals again, but right, this is where oxygen is sp3 hybridized, so it has those sp3 hybridized orbitals making a sigma bond, and that's covalent. Let's add that. And now, so that's different. And then we have hydrogen bonding between another one. So now this little guy would be hanging out over here, roughly. And so this hydrogen is partial positive, right? Again, it got stripped off by that very electronegative oxygen. So it's basically a positive charge. Then we said this oxygen, well, it has those lone pairs, and it's electronegative, so it has all the electron density. So it's partial negative, And so now we have that negative and positive charge creating our hydrogen bonding. And of course, water has 2 opportunities to hydrogen bond. So now I could do it to another water. And again, they're all just kind of floating around. So then this would be another H bond. And again, compared to our covalent bonds there. So does that make sense to everybody? All the pieces slowly coming together. And so your book, I believe, throws in this other attractive force, which isn't normally talked about. Usually you talk about like the 3, the London dispersion, the dipole, and then the hydrogen bonding. But it throws in this ion-dipole interaction. So if you see this, this is even stronger than H bonding. And this is now kind of explaining why our ionic compounds dissolve very readily in water. And again, I think we've seen kind of this illustration before. But now this is showing kind of the attractive forces. So it looks like we had sodium chloride in there. And then the sodium we mentioned. So this is a positively charged cation. And so all the water molecules will kind of orient the oxygen end, the negative end, towards the sodium. So we have that, again, negative, positive, basic interaction. So it totally surrounds and solubilizes that sodium cation. And again, same thing happens to the chlorine anion now, except, of course, the difference is that the hydrogen positive ends are going to be oriented towards the chlorine, solvating that. And so the ion dipole, it doesn't really come up unless we're talking about like ionic compounds. But and so now this is just a summary. And you can see, of course, the increasing strength on the side. So again, we said the dispersion, all molecules have them. So even if you're talking about water, so water has, you know, London dispersion forces, dipole, and hydrogen bonding. So all 3. And then again, dipole, we said that was only present in polar molecules. We have that permanent dipole hydrogen bonding. Again, write it down. It's only when you have hydrogen bonded to fluorine, oxygen, or nitrogen do you have that special case where you have that basically positive hydrogen that can go ahead and bond with another, either oxygen, nitrogen, or fluorine on another atom, or molecule, I mean. And then again, your ion dipole, which for now basically just says, you know, why ionic mixtures dissolve very readily in water. And so looking at this chart, so now this is comparing kind of group 4 and group 6 compounds, and they are arranged with increasing molar mass roughly, except what's the anomaly and why? I'll give everyone a few minutes to look at this. So what's the anomaly? And of course, if you're online, feel free to type in your answer in the chat. So which one doesn't fit the trend and why? So water, and so why doesn't water fit the trend? So hydrogen bonding, exactly. And so if you notice, so we didn't do any fluorine compounds, there's no nitrogen compounds either. And so all of these just followed with their increasing mass trend. So of course we went from sulfur down to the one below, selenium down to tellurium. That all followed the trend, but of course water has the highest boiling point, all because of those two hydrogen bonds. And so here's just another graph. I can zoom out appropriately. And so now we have all these 3 anomalies. And so now what do those 3 have in common once again? So hydrogen bonding, so H2O, HF, and ammonia. All of those have hydrogen bonding. And they all have that same issue where they're very small. We would expect them to maybe have a much lower boiling point, but now they all have a high boiling point with that hydrogen bonding. So again, ammonia also has that phenomenon. And so again, you can compare, you can just see the noble gases that are completely nonpolar, and then comparing, so all these tend to be more nonpolar. So you have methane, so methane's right nonpolar, and so you can see why that one has a pretty low boiling point. And so again, we might expect ammonia to be there, except for hydrogen bonding completely changes it. All right, let's look at surface tension, because I brought at least materials to do a small, if not lame, demo. I figured we might as well do the demo. And so let's talk about surface tension. So what is kind of surface tension? What do you know about it? Yeah, I see people making. So what does it kind of mean? Or what do you notice? You want to describe it, Sandra?
Like with water, it sticks to itself.
Exactly. So it's basically, right, when you have surface tension, you have greater surface tension when a molecule tends to stick to itself. And so what it's trying to do is minimize the surface area. And so you were all describing how water tends to really beat up and do that. And so surface tension is also related to hydrogen bonding. And so again, you have all this intermolecular forces. And so if you have greater intermolecular forces, that'll give you a greater tendency to have increased surface tension. And so this is comparing H2O, which has a surface tension of 72.8 millijoules per meter squared, versus this is benzene. So I didn't bring benzene today, but this is 28 millijoules per meter squared. And so this is really the key point, and then we'll look at a little demo. So the stronger the intermolecular attractive forces, the higher the surface tension. Again, that's why you think of water tending to beat up. And then if you start raising the temperature of any liquid, so again, this goes for water or any sort of liquid, right? Increased temperature means increased molecular motion. That's not a good thing, because now you're increasing the kinetic energy, so that starts to disrupt those intermolecular forces. And so now that increases your kinetic energy, And increased molecular motion means it's easier to stretch the surface, so that kind of disrupts your surface tension. But now let's compare, and I wanted to do this just because not everyone has done this before. But I know some people do this experiment in maybe like middle school or high school, where it's like, how many drops of water can you get on a penny? But then we'll compare water versus, so I have cyclohexane. Oh man, I just realized I need to fix my setup one day. Let's see how bad this works. Because you all in the class can't see. Okay, that kind of works. And so what we can do, and I apologize for the in-class people. So now I have water in this pipette. And so let's just compare. So right away that water is beating up. It's hard to see. Come on. Can you see that water beat it up or no? So that's water. Need to work on my camera. Let's try cyclohexane. And so I picked cyclohexane because I was going for something non-toxic. So I didn't want to bring benzene because benzene is carcinogenic. And so you can, I don't know if you can tell already, it's not beating up like water. My penny's already full. Oh, oh. Still managing to put some on there. Oh no. My cyclohexane shot out. Uh-oh. So now it kind of displays some of my water. I'm making a mess too. Try to redo this water. So I don't know if you can tell on the camera, but you can come up maybe after class too to look at these, and we could play with them more. But basically, the cyclohexane, you know, it fills up the penny, and then I kind of got it running everywhere. So it definitely didn't form as high of a bubble versus the water, but now I kind of messed up my water with all this cyclohexane. But the water made a nice bubble. It's kind of hard to tell. It maybe work as well as I'd hoped, camera-wise. In hindsight, I should have grabbed a paper towel, but let's just use this.
I was gonna say some right there too.
Oh, whoops. Okay. So if you want to look at this, we could play with it after class, since my demo was perhaps hard to see. And it's also why kind of bugs can walk on water, or you could float like a paper clip, for instance, if you were careful. And so we would normally expect maybe like a paper clip or a bug to not be able to float on water or walk on water, since their density is probably greater than water. But you can still float like a paper clip, for instance, if there's enough cohesion, so there's enough intermolecular forces keeping the water molecules all together, even though you have something heavy sitting on top. And so again, that's why your bugs can walk across the water too. Any questions on this one, on surface tension? So viscosity is also related to surface tension. And so again, same thing. So if you have larger intermolecular attractions, you have a greater viscosity. And they're given in these funny units. And so just to kind of give you some context, so water has a viscosity of 1 centipose, or poise, and that's at room temperature. So of course, if you heat it up, same thing, that's going to now decrease your viscosity. But usually you measure viscosity of different substances. So here's all the alkanes for comparison. So pentane has the smallest viscosity compared to nonane, and that makes sense. So we said increase molecular forces from these longer chains. And so again, we see that same trend in viscosity. So stronger the intermolecular forces, the higher the viscosity, so just keep emphasizing that. And the more spherical the molecular shape, the lower the viscosity, and that makes sense. That follows along with what we said about attractive forces, that if they're small, right, there's not a lot of surface area, and so that makes sense why that would lower the viscosity, versus if you have more surface area, we said that was greater attractive forces, and of course that's going to lower the viscosity as well. And so same, again, concept, you raise the temperature, increase kinetic energy. Increased kinetic energy, of course, disrupts intermolecular forces, and so that would reduce the viscosity. So just all same sort of things again. And so something else that's also related is capillary action. And I always like to remind people, like one of Einstein's first papers was actually on capillary action. So, you know, if you ever feel bad about yourself, don't, since the bar of producing science was pretty low at the time. Like, can you imagine if you could write a paper about capillary action? Easy. Anyways, much more difficult to find new science all the time. But all capillary action is the ability of a liquid to flow up a thin tube. And I'm sure you've seen this phenomenon all the time. You can see it, you know, when you were a kid with straws, dipping them in there and how some of the liquid sticks in. You saw it with your TLCs. You dip your TLC in and the liquid flew up there. And so the liquid rises up the tube until the force of gravity counteracts the capillary action. So the narrower the tube, the higher the liquid will rise. And so here's this quick comparison with the narrow tubes. And so you have both cohesive and adhesive forces. So cohesive holds the liquid molecules together. And so we usually see that with water, how it's always held together. So that's why it makes that meniscus. And you would read at the bottom of the meniscus for water. And then you also have adhesive forces, and that attracts the outer liquid molecules to the tube surface. And so those adhesive forces pull the surface of the liquid up the sides of the tube. And so mercury, for comparison, has stronger adhesive forces. And so it makes its meniscus kind of looks upside down, basically, compared to water. So it goes, convex instead of concave. So for mercury, you'd be reading at the top of the meniscus. And again, all that drives that is the difference between the cohesive and adhesive forces. And so now we mention it here. So the meniscus, the curving of the liquid surface in a tube, is due to the competition between adhesive and cohesive forces. So the water is concave. Again, it goes lower since water adhesion to the glass is stronger than the cohesion to itself. I think I had that backwards. So I guess water, the attractive forces kind of help draw it up versus mercury. So mercury's cohesion to itself is stronger. So it's trying to cohese to itself versus the glass. And so this is apparently due to metallic bonds are being stronger than intermolecular attractions. And so the other thing that's related is vapor pressure and boiling point. And so we saw this with lab. So vapor pressure is just the pressure exerted by the vapor when it's in dynamic equilibrium with its liquid. And so we had mentioned before that, you know, any sort of pile of liquid, so a cup of liquid, it's not actually just static here. If it's an open system, then we have some sort of equilibrium, right? And we said, well, some of those molecules do have enough kinetic energy to essentially escape and become a gas. And so if you have a substance then with weak attractive forces, so the weaker the attractive forces, the more molecules will be in the vapor. And so again, weaker attractive forces, the higher the vapor pressure. And the higher the vapor pressure, the more volatile the liquid. And so that's kind of the issue with either like ethers or even like ethanol, for example, of why these can be dangerous and flammable, or even what I always say, like, this is why you get hit in the face with ethers. Or even, like, you probably never work with ether, but, you know, if you open, like, a bottle of wine, for instance, versus, like, a bottle of water, you know, you really get hit in the face with that ethanol, right? You guys know what I'm talking about? And so all that is just, right, ethanol has greater vapor pressure than water, for instance. And so you kind of get all those ethanol vapors in your face. So it can become an issue, like opening up a can of diethyl ether, for example, in the summer. That's going to have a lot of vapor pressure. So you open it up. So ether has a pretty low boiling point to begin with. And so you open that can up, and of course it can kind of hit you in the face with all those vapors. But then, you know, some of the issues and the safety concerns can come in if you have like an open flame, right? And then you have those ether flames, and you have ether everywhere. So you can like light the ether on fire and potentially like light your whole bucket of ether on fire. So that's always why you're careful with open flames. So same thing with ethanol. Like this is where I think biologists get into trouble, since they have to sterilize their little inoculating wand with ethanol. So they're like sterilize it with ethanol and then be flaming it and kind of go back and forth. And it is easy to accidentally set your whole alcohol on fire if you're, you know, not being careful. And again, ethanol with the increased vapor pressure could have your fumes coming up, and the next thing you know, right, your whole ethanol can is on fire. So always, you know, minimize your hazards. You want open flames away from your organics, again, simply because you don't want all those vapors accidentally catching on fire. And I forget what demo it is. It's something that's like chemistry and high school teachers do, but then there's like a danger of fire because of the ether could reignite and then cause a big explosion. And so this vapor pressure curve, I think I briefly mentioned it before, but here's just the relationship that we're talking about. And so the key point, so we have vapor pressure on the side. So we said, right, 1 ATM is 760 torr, so that's this line right here. And let's just relabel that, so 1 ATM. And so all this is saying is this is the vapor pressure as temperature increases. So we had looked at water for our lab. That's why I said, you know, ask Google the answer, kind of. So this is a trend that it takes. And all these take this trend until you hit the normal boiling point. And so once you hit that normal boiling point, you can say, well, this is my boiling point, right, when my vapor pressure is equal to my atmospheric pressure. So for water, that's obviously 100 degrees Celsius. Ethanol is 78, and ether is 34. Again, all we're saying, we're increasing the temperature, that increases kinetic energy until, of course, more and more of those molecules have that appropriate energy to escape the liquid and go into the gas phase. All right, questions about this? Okay, I think we'll probably stop here. We don't have too much more. I'm just kind of glancing. So I skipped the main math. So I don't want to start that now, even though we have 10 minutes, because I don't want to rush it. So we'll probably save this heating curve for first thing on Thursday. We'll go through the math. And then that will lead us to these phase diagrams, which isn't too hard. And then we'll talk a little bit about crystal structures, but we don't really get too into these. And yeah, so then we'll just briefly talk about solids for the rest of the chapter. So like I said, let's end here for today. So we'll pick up on all the math. So maybe look over these heating curves too, so you kind of know what to expect. And we'll go over all of them on Thursday. And then, oh, I have homework and printed out labs, so if you can grab one, grab it. And then I have graded quizzes, so if you came in, I'll try to get those to you. And then don't forget about clubs days. And thanks for coming online. I'm going to go ahead and end the stream. And just email me if you need anything.